Hey there. In this lab, we're going to be looking at the impulse momentum theorem. The impulse momentum theorem relates a quantity called impulse, which is essentially the amount of force acting on an object multiplied by the amount of time that force acts on an object. How that impulse relates to the change in momentum of that object that has an impulse acting on it. Do an example. A good one is a baseball bat striking a baseball. You have a baseball that's coming into home plate, and then you have a bat that hits the baseball and delivers a force over a certain period of time to the baseball. The amount of force that the baseball bat delivers to the baseball multiplied by the amount of time in seconds that the baseball is in contact with the bat is the impulse delivered to the ball by the bat. Essentially, impulse is simply force multiplied by time, where time is the amount of time that force is acting on some object. In the case of our baseball bat acting on the baseball, the impulse we would call the impulse delivered by the bat to the baseball. And that amount of impulse is going to be the force that the bat hits the ball with multiplied by the amount of time the bat is in contact with the ball. That's the total amount of impulse delivered to the ball by the bat. That impulse, according to the impulse momentum theorem, is equivalent into the change of momentum of the ball. Say that one more time. The impulse delivered by the baseball bat to the ball is equivalent to the change in momentum of that baseball. The baseball, you can imagine, is coming in this direction, say the positive direction, and it has a positive momentum. The baseball bat then hits the ball, delivering an impulse, which changes the momentum of the ball. The ball will go in the opposite direction now, so instead of having a positive momentum, it now has a negative momentum traveling away from home plate. The amount of change in momentum of the ball is equivalent to the impulse delivered by the baseball bat onto that baseball. We're going to look at this relationship between impulse and momentum with one of our carts that has the spring plunger attached to it. We're going to leave the spring plunger out, and we're going to send the cart down the track, and then the plunger is going to hit a force sensor right at the end of the track, and so it's going to hit kind of like a baseball would hit a wall or something and then bounce back off. Our cart's going to hit spring first onto the force sensor and then bounce back the other way, thereby changing its momentum from being a positive momentum to a negative momentum. And we'll be able to see how much force is acting on our spring when it hits the force sensor. And our force sensor will also tell us how long, for how much time, that force was acting on our cart. With that force and that time, we can determine the impulse. The symbol for impulse is capital J. But remember, impulse is really just force multiplied by time. We'll get that force and time from our force sensor, and then we'll also look at the momentum before and after the impulse is delivered to our car by looking at the position versus time graph from our motion sensor. We can use the motion sensor and the position time graph because we can just look at the slopes on the position time graph to get the incoming velocity of our cart. We can use that to get the initial momentum of the cart. And then after it hits the force sensor and bounces back the other way, we will see a different velocity and use that to calculate the final momentum of our cart. Remember, change in momentum is going to be final momentum minus initial momentum. Be careful with your plus and minus signs. And change in momentum should be equivalent to the impulse that's delivered, measured by the force sensor. We'll do 5 trials. I'll simply just change the amount of mass involved so we can get some different measurements. First, we'll try it with just the cart, and then I will subsequently add each of these blocks one at a time. So we'll end up with 1, 2, 3, 4, 5 trials, and we'll put the mass of these guys is about 500 grams or so. We'll put the mass of these guys up there, and we'll have a picture with the triple beam balance for the mass of this cart. Let's look at the total setup. We've got our trusty spring cart here once again. I just have an index card there to help the sound waves bounce off of it because we have our motion detector over there, which is pointing down the track, and to the right is the positive direction. So we'll see the overhead view of the cart moving down the track, moving in the positive direction. And then over at the other end, we have the force sensor. Let's go take a look at that. The force sensor usually has a kind of hook that goes in here. I just took that out, and this is basically a piston. When you push it in or pull it out, it measures the amount of force in newtons that's doing that push or pull. I just put it on the track so that, as you can see, the plunger from the spring, this little piston here, is going to come along. It's going to contact the force sensor and depress a bit, and then it will expand again and shoot off in the other direction, and we will be able to get a nice precise reading of the force and the amount of time acting on our cart. Clamped it on there gently so it doesn't fly off, obviously. All right. We also have our 4 weights here ready to go for each additional trial. All right, everybody, this is our setup. I had to move into the office out of the classroom, but what we're going to do is have a cart that's going to move down the track, and I'm calling to the right now the negative direction. So initially this cart is going to have a negative momentum because it will have a negative velocity. It's going to come down here until it reaches this force sensor. This is where the force sensor is, right at the end of the track on the right side of the screen. And when it hits that force sensor, the spring is going to compress, and there's going to be a force pushing back on our cart in the positive direction that's going to send our cart back the other way. And it'll have then a positive velocity and a positive momentum. So we're looking to investigate the relationship between the impulse, which is the amount of force applied on our cart multiplied by the time that that force applies this way. And we're seeing if that impulse is going to be equivalent to the change in the cart's momentum. Remember that our change in momentum, which we could write as delta P, is going to be equal to the final momentum, P final, minus the initial momentum. So in this case, we're going to have an initial momentum that's negative because to the right is the negative direction. So that's going to be the initial momentum. And then it's going to bounce off this force sensor, receive an impulse, so that changes its momentum, and now it'll have a positive momentum going back to the left. So our change in momentum is going to be final, something positive, minus the initial momentum, something negative. So we should always end up with some final positive momentum minus some negative initial momentum, and we're checking to see if that's going to be equivalent to the impulse delivered to our cart. We're going to start off with our first trial, which is going to be just the cart. None of the mass is on top of it. We have 4 masses we're going to add for each additional trial, adding 1, then putting 2 on top of the cart, then 3 on top of the cart, and then all 4 on top of the cart, which will give us trial number 5. But we are starting right now just with our cart. We're going to set it up at the end of the track here, right off the edge of the screen. I'm going to send it down, flying towards the force sensor. Our force sensor will record the force and how long that force acts on our cart in seconds, from which we can get the impulse. And then we'll also use our motion sensor, which is over here. Just look at it with our camera real quick. Yeah, see, motion detector is over there. We're going to use that to look at our position time graph to see what the velocity initial and velocity final of our cart is. So let's start off the very first trial with just the cart. Okay, not bad. This is pretty clear. So remember, we're moving in the negative direction first, so we see a negative slope, and from this here in the blue position versus time graph, if we do a curve fit on this linear function here, we can see what the slope is, and that slope is going to be our initial velocity, which is the velocity in the negative direction, before the impulse is delivered to our cart. Let's go analyze that curve fit position. We need to tell it to be a linear fit. And now we have, given by the slope parameter m, the initial velocity of our cart. This is just the cart, so when we calculate the initial momentum, we should have our initial velocity, which is a negative velocity right here, multiplied by the mass of our cart. Let's go look at the final velocity of our cart. This will be used to calculate the final momentum. Here we go. Now we're selecting the positive slope, so that's traveling back to the left after an impulse has been delivered, and our final velocity of the cart is given by our slope parameter here, m, and that value is 0.39199, that's in meters per second, is our final velocity. Multiply that by the mass of our cart, and we get the final momentum. You're going to need to find out what the change in momentum is, so that's going to be final momentum minus the initial momentum. Tells us our change. All right, now we got to figure out what the impulse is delivered to this cart. So we're going up to the top graph, which is in red, and this is, notice the y-axis is force and x-axis is time, and that's exactly what impulse is, force multiplied by time. We need to zoom in, and you can see we've got something that almost resembles a triangle here on our red force versus time graph. Now, the force is changing. It's not a constant value for the force. So in order to figure out what the impulse is, there are a couple things we could do. We could highlight this region and tell the computer to calculate the average force, or we can just figure out what the area under the curve is right here. So we want to find out what is the area between this red function and the x-axis, and that will tell us the impulse, because the area, well, that's multiplication if you're finding the area. So the area under the curve is going to be whatever's on the y-axis, which is force, multiplied by whatever is on the x-axis, which is time. So the area under this curve gives us force multiplied by time, which is the impulse. Now it's kind of hard to calculate the area of some weird shape like this, but we can just tell the computer to find the integral, because that's what an integral is on a motion graph. It's the area beneath the curve, or between the function and the x-axis. So there, right here on the right, we have the value for the integral, which in this case is 0.52449, and that's equivalent to the impulse delivered to our cart. The units there, since we're multiplying what's on the y-axis by what's on the x-axis, since we're finding the area, the units there are going to be newtons multiplied by seconds. So we can say that the impulse delivered to our cart is 0.52449 newtons times seconds, or just newton seconds for short. Again, we're comparing this impulse, which is given by the integral, we're comparing that value to the change in momentum of the cart. The impulse momentum theorem states that those values should be the same. Okay, we're ready for trial 2, where now we're going to put one of these blocks on top of our cart. We'll have the mass up there on the screen for each of our blocks. So this one is going on our cart. There. And so now we have a new mass, and I'm going to push it down the track again just like we did before. I have no idea what velocity I'll push it with. It's just arbitrary. I push it down the track, and we'll see it go down there, and it'll hit our force sensor. We'll have an impulse delivered that we'll have to find again with the integral, and we'll look at our initial and final velocities just like we did on the position time graph in order to figure out the initial and final momentum of our cart. All right, here we go. All right, looks pretty similar to what we saw before. Let's get our initial velocity when we're moving in the negative direction so that we can calculate the initial momentum. There we go. There's our slope parameter giving us the slope of the position time graph, or the velocity for our cart. As it travels in the negative direction, we can use this to calculate the initial momentum. That initial momentum now should be the mass of not just the cart, but the cart plus the mass of this block. That'll be our total mass. And then we need to multiply that by the velocity value we got and see on the screen right now, given by the slope of our position time graph. This is the initial velocity. Let's go back, we'll take a look at the final velocity. It's going to be over here. And there we go, we have our positive final velocity of our cart plus one block right there. Remember, our change in momentum is going to be final momentum minus initial momentum. Now we just need to take a look at our force sensor data so that we can figure out what the impulse is. We're going to zoom in, see what kind of shape we got this time. Wow, so that pretty much is just a triangle. So that's a pretty easy one we could you try to calculate without having to use the integral. Let's zoom in a little more and just see if it actually looks triangular. There might be a little bit of curviness happening over there on the left, but we're going to use our integral calculation to get us the area under the curve. Remember, under the curve means between the function in red and the x-axis. And so our integral is just a way of finding what the total area is. And that's basically multiplying what's on the y-axis by what's on the x-axis. So force multiplied by time, that's impulse. That's why we're finding the area under the curve, which is the same thing as the integral here. All right, so there's our integral value, 0.82442. Units are newtons times seconds, and that is our impulse delivered to our cart. We're comparing that to the change in momentum of our cart. Remember, change in momentum is final momentum minus initial momentum. Okay, we're ready for our next trial, so we're going to add on this block, which has the same amount of mass. Now we got two of them on there. Hopefully they don't fly off. And again, we're going to look at the same stuff. This is trial number 3, cart plus 2 blocks. Let's see what we got. Oh, that was kind of fast. All right, we're seeing a nice consistent pattern here. Let's get our initial velocity, which is negative. Here we go. Okay, we're looking at the negative slope on our way traveling on the track to the right in the rightward direction, which is our negative direction. So we got a negative slope. That gets our initial velocity for our cart plus 2 blocks. Let's get the final velocity now. Linear. All right, there we go. Now our slope parameter is indicating our velocity final after the impulse is delivered to our cart. You can see that right there. Now we're going to go look at our impulse for this one. Again, this is trial number 3, the cart plus 2 of the blocks. I'm going to zoom in. Okay, we get another kind of weird shape. So we're going to highlight. There we go. We want to find the area under the curve because that's force multiplied by time, and we'll use the integral to find that area. So there's our integral, also known as, in this case, our impulse, right there where my mouse is. Compare that to our change in momentum. All right, it's time for the 4th trial. We're going to add another block. All right, so now we got 3 blocks on top of our cart. So our total mass, when we're looking to calculate the momentum, we got mass of the cart plus the mass of the first block, plus the mass of the second block, plus the mass of the third block. All that mass we got to multiply by our velocity to get the momentum. All right, here we go. Okay, let's get our initial velocity right here. Position time graph, so we just need our slope in order to get the velocity. It's linear. We're moving in the negative direction, so we get a negative slope. And there's our initial velocity for our cart plus 3 blocks on top of it, which is trial number 4. Let's get our final velocity. Notice I want to select the portion of the graph that is clearly linear before this noise happens up here. Put on our curve fit that is linear and see what our slope is. And there we go. Our slope parameter indicates our velocity, which is positive. We're moving in the leftward or positive direction. There's our final velocity from which we can get our final momentum. Make sure you include all the masses that are on top of our cart plus the mass of the cart when calculating that momentum. Now we're going to go get our impulse delivered to our cart. So impulse is force times time, so we're back up in the force versus time graph, or the red function. Let's zoom in first, see what kind of weird shape we got. It's looking pretty consistent. Alright, let's find that integral, or the area under the curve, which will be equivalent to our impulse delivered to the cart. Force multiplied by time. Compare that to our change in momentum. Alright, we have one more trial left to do. Now we're going to have all 4 of these blocks on top of our cart. Which don't really fit. That's okay. Just try not to break anything. Alright, let's start our thing. And there we go. Not as fast this time. Okay. That's better. Alright, once again, here we go. We're going to get our initial velocity to calculate our initial momentum. Linear fit. Okay, from that we can get our initial velocity for our cart plus all 4 blocks on top of it. Make sure you use the total mass of all 4 blocks plus the mass of the cart multiplied by our initial velocity to get the initial momentum. Let's look at our final velocity. Moving back in the positive direction. Linear fit. And there is our final velocity given by the slope parameter. Use that to get our final momentum. Alright, last thing to do is check out our impulse delivered to the cart. Let's zoom in, see what kind of shape we got here. A little more trapezoidal now. We want to get the area under the curve because the area is the y-axis stuff multiplied by the x-axis stuff, so that area is force times time, which means it is the impulse. Our integral gets us that area under the curve, as is shaded up in red. There's the result of our integral, or the area under the curve, which is equivalent to our impulse. We're going to compare that to our change in momentum. And that's our last trial, a cart with all 4 blocks on top of it.